Hello, Assalamualaikum. Hi everybody. Now today we gonna learn about duct system design. Welcome to my next lecture. Just wait for a second. Alright. So let's see what we're gonna learn today. We're gonna see the design overview and the methods that we can use in designing our system. Alright, it's very essential that in a design we should take three things into account, which is the space limit. Sorry, here. Oh my god, the space limit. How much space that we have in our plenum or ceiling, and of course in a design we try to minimize the noise. And the third factor is the cost that is specified by the client. We do not want to exceed the cost that is already specified. As I mentioned before in my previous lecture, we can suggest to them what is the best, which design is the best for their building, but it depends. Sometimes due to the cost restriction, customer will reject the suggestion. Alright, the round duct. As we heard from the seminar from Mr. Chung last time, the ratio that we would want to maintain as close as possible to 1:1. That means the width to height ratio, if possible, it should be 1:1, but never exceed 1:3. Alright, and the system, normally for rigid duct we use rectangular duct, and for the flexible duct we use round duct that is near the outlet, near the exit or diffuser. We wouldn't use round duct just for fun. That means if it is not required, or the distributed air is not specified to be for precision, for example, then it is better to use rectangular duct because it is more cheaper. But the disadvantage of a rectangular duct is its pressure drop is higher than the round duct. So in round duct, because due to the round cross section, it has lower resistance. That's why the pressure drop is lesser, and therefore the price of the round duct is higher. And the second rule, normally the width of the rectangular duct should be greater than the height if we have enough space limit, because this arrangement, if the width is greater than the height, then the duct is more stable. Unless we don't have enough space, then we have to turn it upside down. To turn it the other way around, which is height is greater than the width. if only we do not have the enough space. If not, then the width should be greater than the height of the duct cross section. Alright, this is basically a table to see the equal friction rate at 15,000 CFM of distributed air. What we want to show here is actually we can convert the size of a round duct. If we know the size of a round duct and we know the CFM, we can actually know the size of the other form of duct. For example, you know the CFM and you know the equal friction rate, then you can choose the round duct size or the equivalent rectangular duct size by using duct calculator, or as we always mention, ductulator. Or you can also choose, if you know the CFM and know the velocity, then you can also choose the size for round duct or equivalent rectangular duct. The most important thing is we choose the right form of duct, which is rectangular or round duct. A second rule is the ratio of the width to the height of the cross section of the duct, if it is a rectangular duct, must be as close as possible to 1:1 and must never exceed 1:3. And the third rule, it should be the width of the duct should be greater than the height of the duct. Just to recap again. Alright, what does it mean, duct design? Normally, duct design, we want to determine the duct size. What type of material it is, what size it has, what type of duct. You have to take all the factors into account, just like we said before, the 3 factors. Other factors that also need to be considered are the total pressure and also the duct layout. Normally, first we should know the load of a building. Then we should have the total pressure, and we have the duct layout, how many diffusers that you want to use. Then only then you can design your type of duct and also the duct size. You have to know the purpose of the room, whether for example it is an exhaust for chemicals or just for normal room. There are 3 most common methods to size duct. First, it is velocity reduction. Normally we use the velocity reduction method where there is significant velocity differences. For example, after the filter and before the filter. So the distance between the before and after the filter, we use the velocity reduction method. The second method is the equal friction method, which is used for small to big ducting network. And like its name, equal friction method. That means for the whole system, for the most part of the system, we should assume friction rate, friction loss rate, which is equal for all parts of the system, except for the certain part that maybe, like I said before and after a filter. Then we use only for that part the method that we call velocity reduction method. The third method that we have is static regain. This is for large and high velocity ducting system, and it is rarely used because it is quite expensive. Alright, for velocity reduction method, okay, we should assign a velocity to the various section of the duct system, and of course the highest is at the entrance or the supply, the first supply, the first before it is distributed to rooms. Alright, so the velocities in the succeeding or the next section, for example, after it is distributed to room A, then the velocity should be reduced, and after a while, until it comes to section B or room B, it should be further reduced until the lowest at the end of the duct. And the air quantity for each section should be known already, and we have to cross-check the velocity range that is allowable for the type of the building. For example, we have public building, then we should refer the table, how much is the range of the allowable velocity. So then even though we reduce the velocity, it wouldn't be lower or higher than the allowed range of velocity. Yes, this is the table that I mentioned. For example, we have the velocities, recommended velocities for residences, recommended velocities for school, theaters and public buildings, and the last one is the velocity, recommended velocities for industrial buildings. However, in this table also we have the range for maximum velocities. We can see on the left side of the table, we can see it is stated there which section this velocities is responsible for. For example, we have main ducts, branch ducts, risers, filters, and so on. And the velocities that we choose shouldn't exceed the maximum velocity, the maximum velocities that is stated here. And this table, normally we can read from the duct calculator or ductulator. Alright, and there's table also recommended maximum duct velocities for high velocity systems. Alright, it is different than the low velocity systems. VR stands for velocity reduction method. It is empirical, and you have to really judge, you have to give reasons why you select that velocity, because there is no right or wrong answers as long as the velocities is still in range and your selected duct size is does make sense. For example, your flexible duct can never be greater or bigger or equal to the rigid main duct, because then you cannot connect both the main duct and also the branch duct. It doesn't make sense. It simply doesn't make sense. Then your design will be a trash then. Okay, let's see an example. Here it is said that you should determine the ductwork size of a sketch below for public building by velocity reduction method, and I would say this is for low velocity and please calculate the friction factor, or we can call it friction loss, for each duct for its respective length. So you should give your attention to every detail of the question. Just let's say if it is said that friction loss for each duct, just like that, then you can give your answer per 100 feet. But if it is said here friction loss, please find friction loss for each duct for its respective length, then you have to times with the length of the duct. For example, for the section B to C, the length of this duct is 14 feet. That means if you have 0.1 friction loss, if you set your friction loss rate for the section BC is 0.1 in the equal friction method, then you have to times 14 feet with 0.1 per 100. I hope you do not confuse here. I hope that you understand what I'm trying to tell you. But since this is a velocity reduction method, then yeah, because you need from the velocity reduction method and you know the CFM, then you can select the size of the duct, and you also can read the friction factor from duct calculator or ductulator. Then you have to times for example 0.1 per 100 length, per 100 feet length, times the 14 feet, so that you get the friction factor for the whole length of the section, for example here BC.